Hello, I'm Richard Patterson and I'd like to welcome you to Series 2 of these videos presented by IPC Irwin and CPD Science. And in this episode, we're going to look at the red laser rayboxes. They come in two versions. This one uses a charger adapter, and this more portable version has got two AA batteries. As with any Class 2 laser, you need adult supervision, and of course no one should ever look into the red laser source. So the advantages of these over your traditional raybox is that firstly they run a lot cooler and the lamps will not need replacing. You can also work in a lab that has no blackout. So we'll now have a look at traditional raybox experiments using the red laser. So as we can see here, we're going to look at the laws of reflection in a plane mirror. We're using a scaffolding. It's a printed protractor, and this is going to help some students align the rays and take the measurement to work out the angle of reflection. Of course, many students, you wouldn't need this, and you just use a plain piece of paper and pencils and rulers. I've aligned the instant ray coming in over 45 degrees, so I'm going to put in this plane mirror like so, and if we get that exactly where the ray hits the normal and the plane mirror, we can easily read off that the reflected ray is 45 degrees to the normal. And I can use the raybox for a different angle of incidence. Here we're using 30 degrees, and the reflected ray, if I make sure it's exactly aligned, is reflecting at 30 degrees. We're working in a room with no blackout, so the red laser raybox clearly is a great advantage over the traditional model with the filament lamp. So moving on to curved mirrors, well, the red raybox clearly shows that for this convex mirror, I'll just put in some extra support there. The instant ray converges, and we can go on and look at the focus of the mirror. And if we reverse the mirror and turn it into a diverging mirror, like so, we can see the instant ray diverges away. In this demonstration, we're going to see how the raybox can be used to investigate refraction using this rectangular perspex block. The instant ray is entering the far side of the glass block and emerging on the other side, but it's been displaced. Refraction has taken place, the ray has bent, and if I remove the glass block, you'll see how the ray would have just passed normally through the air without the refraction. Looking at the two types of lenses we use in ray optics, we've got a concave lens and a convex lens. Convex lens will converge rays. The concave lens will diverge rays. So using our raybox, we'll try the convex lens, and hopefully if we have that incident on the lens like so, we can see that the ray is being converged. Swapping that for our concave lens, we can see divergence. The last demonstration is looking at total internal reflection and critical angle. So the raybox is now sending an instant ray into this semicircular perspex tray, which we filled with water, so it's acting as a prism. And the refracted ray is coming out this side there into the air. If we gradually rotate the prism, the angle of refraction is increasing, and at this point the ray no longer emerges from the prism but travels along the boundary. If we further rotate the prism, we get the ray refracting off this surface here, and we call that total internal reflection. And by using this bright red laser ray box, this is very clear to see even in a lab that's got no blackout.